Okay, so we're doing question 1 on page 56, yellow pages in the notebook. So this question 1 deals with the simplest case where you have an alternative hypothesis that's just an all or nothing. So the person, the null hypothesis, for example, would be the person does not have a disease, and the alternative is they do have a disease. The null would be no fire, the alternative would be fire. There's just one simple alternative, as opposed to later on when we do power calculations where there's a whole range of alternatives. So this question is about airline security tests, screening tests to see if somebody is carrying a weapon or not. So it says in the book here, this is in your practice exam, that screening tests are perfect. When the passenger has a weapon, there's a 99% chance the alarm will correctly go off when the passenger has a weapon. When the passenger does not have a weapon, there's a 12% chance that the alarm will incorrectly go off. So we're going to put this in the context of a significance test. And it says, the first question, question A, says, the conventional null hypothesis is what? What's the null hypothesis? I just said it before. The null is no weapon. That's what the null is. Like no disease, no weapon, no fire, just the ordinary stuff. So that was option 4. Now, and the next option says a type. Well, first of all, let's make a chart here and see what's going on. All right? So the conventional, we can say, all right, so there's a truth, the truth right here, and that's either, the truth is either the person has a weapon or does not have a weapon. All right? So I can say positive, has weapon, positive for weapon, or negative, no weapon. All right. And then the null hypothesis is always you're assuming no weapon. Null means no, so no null. Just think like that. That's the null hypothesis. And the alternative hypothesis is a super simple one that they have a weapon. They have the disease. There is a fire, etc. And then we make a decision. And our decision, this is our decision over here, and we can either decide, yes, there is a weapon, and the alarm will go off, or no, there's not a weapon. So that's our decision, right? And so now we can fill in with this in this chart. So this says when the passenger has a weapon, right here, there's a 99% chance that it correctly goes off. So this is 99%, all right? So that means in the situation where where he has a weapon and you make a decision, either the alarm goes off or it doesn't, that has to add up to 100%. So this is a 1% error. They incorrectly, right? And then over here, just reading that, 12% chance when the passenger has no weapon, it's like under the null when it has no weapon, there's a 12% chance that you'll make a mistake and decide that positive for weapon. So there's 12% here, which means 88% here. Because the columns here, this is the truth. You're either in this situation, so you either make the right decision or the wrong decision, so this is an error, or you're in this situation, and you either make the right decision, negative, right, or the wrong decision, so that's an error. All right. So that's the situation we're in, and so now these errors are called either type 1 or type 2, so which is which? Well, think of it this way. You assume the null hypothesis. That's where you start. Innocent person, nothing's going on. Assume this null hypothesis, and the only error you can make is this one. It's called a type 1 error. How are you going to remember that? Type 1, just think that you start with this null. And that's the first type of error you can make, when there's no weapon. And then The other type of error you can make is suppose the person really does have a weapon and it fails to go off. So that is a type 2 error. Right here. Type 2 error. So that's the idea. So now the questions ask, a type 1 error can occur only when? Well, only under the null. Only under the null can you make this type of error. So that's your answer for that question. That's B, would be only when the null is true. Can you make that type of error? And only when the null is false can you make a type 2 error. All right. So part C says a passenger comes in without a weapon. So they're in this situation without a weapon. What's the probability that the screening will make a type 1 error? Well, it's 12%, right? 12%. What's the probability that it will make a type 2 error? Well, can it make a type 2 error? It can't. If it comes in without a weapon, we're in this situation, so it's impossible to make the other type of mistake. So that would just be 0. And similarly, it says a passenger comes in carrying a weapon, and so the probability of a type 2 error is 1%, and you can't make a type 1 error. You can only make a type 2. That's type 1, that's type 2. All right, so that's part 1, and then it says, question 1, and what else? If you change the cutoff of the screening test to decrease the probability of a type 1 error, what happens to the probability of a type 2 error? Okay, so if you make your screening so sensitive that it will detect anything that's vaguely like a weapon, like you carry, I don't know, you're carrying a little metal on your watch or something, anything, well then it's going to, if it makes it so sensitive, then it's going to really increase the probability of which type of error, well, when you don't have a weapon, will be just so sensitive, it's just going to go off no matter what, and that's going to increase this probability, but it will catch, of course, it will decrease the probability of a type 2, right? Error. And then if increasing one decreases the other. So that's the answer there, so it will be increased. Now let's move on to question 2. Question 2 deals more with, in general, more general situation where there's a whole range of alternative hypotheses. Question 2 starts off saying, a significance test is performed to analyze the results of a randomized experiment to test if some drug worked. So we're comparing cure rates between a drug and a placebo. So the null is the same, that there's no difference between the drug. I mean, the null is always the hypothesis of no effect, so there's no difference between the drug, how well the drug works and how well the placebo works. It doesn't do anything. But then the alternative is there's a huge range of them. The drug could work, cure 10% of the people, 20% of the people, 30%, 40% could cure everybody. So here's where we start doing power calculations. This is the more typical situation. All right. Okay, so this is question 2, and we're trying to see if a drug works. So we're looking at a randomized trial comparing a drug to a placebo. So the null is the difference in the cure rates between the drug and the placebo is 0, and the alternative is no, the drug worked better. All right, so the first question says, suppose that the null is true. What's the chance that researchers will make the wrong decision if they set alpha equal to 0.05? All right, so if the null is true, let's say under the null, what we're measuring will be the difference in cure rates between the drug and the placebo, and we'd expect, if the null is true, we'd expect to get 0, right? Both as a z-score and as a difference. And when we say at what point, how big a difference do we need to see between the drug and the placebo to say, okay, we've seen enough evidence and we are going to reject this null. We're going to decide that the drug works. So when we set alpha equals to, this is 5%, we say, okay, what that means is we're going to set it, and it's a 1, we're going to set it so that 5% of the time we'll say it's beyond a reasonable doubt, and if it's on this side, we'll conclude that the drug worked. If it's on this side, we'll say no, the difference is bigger than 0. And this right here is 5%. Now it's a one-tailed test because we specified the direction. So all the errors contained in here. So what's the chance that researchers will make a wrong decision? Well, 5%. So setting this, we're saying we're accepting a 5% error rate is what it is. We're saying 5% of the time we're going to be wrong when we set alpha equal to 0.05. If we wanted to be more sure, we'd set it at 1%. This is beyond, at this point we're saying it's beyond a reasonable doubt. Okay? So the answer is, let's see, it was a multiple choice, so the answer was 5%. That's your answer. Those two things are the same. Now, what if the null is false? What if the alternative is true? Let's say the drug really worked. What's the chance we're going to make a wrong decision and decide the drug didn't work when it really did? Okay? So that says, okay, so if it really, we're going to decide on this side, we'll be deciding on this side, and we'll be wrong. Well, what's the chance of that? Well, doesn't that depend on how well the drug works? You'd say, okay, you think that if it works, let's say it works, it's not 0. Let's say the null is true, there's a different distribution, right? Well, that depends. If it works really well, is very far away, then there's just going to be a tiny chance of making a mistake. But what if it's not there? We have to specify a particular alternative, how well we think the drug works. If the drug only works a little bit better, you know, maybe it works right, just a little bit better, well then we're going to make a huge error. So it depends on the specific alternative that we set. That will change the type 2 error. Okay? So now, let's see what the next question is. The next question says, suppose we set alpha, this is C, then at 10%, then the critical value of our test statistic is such and such. Okay, so if we set, this is part C, and the question is, if we set alpha equal to 10%, that's a null cutoff at 10%, then the critical value, this means Z star, the critical value, is equal to what? All right, so alpha equal to 10%, we still have this one-tailed test, means we're willing to accept this 10% error right here. So we're just looking for the Z-score that corresponds to 10% right there, right? And so we're going to have to look in the table that you're going to be provided on the exam. You'll have the middle area, and you'll find a Z-score corresponding to a particular middle area. So 10% here, imagine, would be what? You'd have to have a 10% in the tail there, and what it would leave is 90%, 90% all the way to there, but 80% in the middle. Okay? So you'd have to look up a middle area of 80%, which would give you about 1.3. So it's the Z corresponding, sorry, I think you probably understand that. I don't think I have to go any further than that. All right, so now what's the next question? The next question is D. We want to repeat this with a two-sided. All right, so let's say this was not greater than, but it was just not equal to. That means that this same 10%, this is part D, so repeat with two-sided. Two-sided alternative. So now we're in the situation where we want to figure out where the null cutoff is if we're willing to accept a 10% error, this is still here, 10% error, but we want to say it could be on this side or that side. So 10% divided between the two tails. So 10% total error would be 5% on this side and 5% on this side, because we don't know. We know less. We don't know if the drug works better or if the drug works worse than a placebo. We know the drug has some effect, maybe. I mean, this could happen. You know the drug is going to do something, but you don't know if it's going to kill people or cure them, right? I mean, that's how some drugs, you just don't know. You know it's going to do something. And so you want to say, okay, we're going to say the drug, so we don't know, and so we have to get, so it would be 5% on either, and that would mean 90% in the middle, which would be 1.65 and negative 1.65. So the critical value of Z would then be 1.65. All right, let's see what we have to do next. That's D. And then, if E says, if we computed a p-value using a one-sided alternative, but now want to change to a two-sided alternative, how would the p-value change? So this isn't talking about setting a critical value. It's just saying our sample landed a certain distance. So this is part E. Okay? So these are for critical values. This is Z star. We're setting it here, and we're saying we're going to, the total area equals our 10% significance level. Now, for this one, we said we computed a p-value using a one-sided alternative. So that meant we computed some p-values, so we got some, here's our distribution. We expect to get right here. And then our sample, let's say we thought it was one-sided this way, our sample landed somewhere, right? I don't know, far. Let's just say it landed right there. Well, the probability, the p-value is the probability that under the null, we'd see this extreme value or more, this tail, just by the luck of the draw, right? So that's it with the one-sided, right? Let's say we computed that. We called it p, whatever that value is. We computed it. Now they say, wait a minute, Ellen, you should have gone back and done a two-sided alternative. Well, I have to go back and do this again? No. If I had done a two-sided alternative, I would have had to say, hey, I didn't know it was going to land on this side, so this is for the two-sided alternative. This is if it's one-sided. And now let's say, all of a sudden I got to change to two-sided. I don't have to repeat the experiment. I can just say, okay, the two-sided said, the drug, okay, so if it doesn't do anything, we know the difference is 0. But the two-sided says, hey, it might do better, it might cure you or kill you. You don't know. So we don't really know which direction it's going to land in. So let's say we got the same exact thing right here. Well, it landed there, so we have to count that p. But the idea is that it could have just as easily landed on that side, because our alternative, we're just saying it's far away. What's the chance that it's more extreme in either direction? Because that's what we're saying with the alternative. So then, when it's two-sided, that we don't know. So the uncertainty is on both sides. So it's twice the p-value. So your answer would be the p-value would be multiplied by 2. All right, let's move on to the next page. Let's do, sure. Okay, so now we're going to take these power calculations a step further, and we're actually going to do power calculations. So let's look at question 3 on page 57. All right, question 3. So let's do that. And, all right, so this is where you're actually going to do power calculations. And let's just write down what we know with this. So with the power calculations, excuse me, what we're trying to do is we have a null hypothesis that says there's no difference, and then our alternative specifies the minimal effect, or that we want to see, that we think we can detect. Maybe I should just, here, let's write down this. So you have some effect size that you're trying to detect. We'll call it D. And what this effect size is a difference between your hypothesized specific, hypothesized alternative, and the null, a distance. So, for example, if you think the drug could cure at least 10% of the people, all right? So it's this distance that you're trying to detect. That's your effect size. And you're going to be relating it to a distance in z-scores. And the distance in z-scores we're going to split up into z alpha and z beta. Okay? These will all be absolute values because we care about distances. And then to match these two up, we need this conversion factor, which is the standard error. All right, so that's the idea. And then we're going to be doing, at first we're going to be looking at, given a particular experiment with a set significance level, we are going to look at what our type 2 error is. So we're going to do that calculation under a specified alternative, figuring out what the size of our type 2 error is given our type 1. That's the first part of it. So and then the second part, another thing that's more commonly done, is to figure out, given a set significance level and given a set power, given a set type 1 and type 2 errors, basically, and the effect size you want to detect, well, how many people should we sample, or how should we adjust our standard error? How precise a measurement do we need, basically? How much precision do we need, and how many people, or what should our sample size be in order to detect a specified hypothesis? All right, so let's just start this example, and it's a simple one-sample z-test, basically. All right, a university claims that the ACT scores of its freshman class of 7,000 students follows the normal curve with an average equal to 29 and a standard deviation equal to 3. So that's the null hypothesis, we'll put it up here, is that the population average, we'll call it mu, the population average equals 29, and the population standard deviation, sigma, equals 3. Population. So that's all 7,000 people. So that by the average of the 7,000 students is that. And the alternative is that no, the university's lying. They're inflating their ACT scores, and we think it's only 27.5 or less. So we'll set that as our alternative. And then it could be less than that. So this is the maximum alternative, it could be less than that. And we'll have the same population standard deviation. All right? And so this is the null box here is imagine all 7,000 students in there. All right. And now the question says, all right, and then what would I expect? Of course, what I'd expect my sample average to be would be what? 29 under the null. With a standard error of what? So let's do that. So part B says, assuming the null to be true, I'd expect x bar, our sample average under the null, to be equal to 29. And the standard sampling error of the average, when I sample 25 people out of there, we have a sample of 25, so we should put that down here. Here, n equals 25. It's going to vary. And that's going to vary as divided by the square, the bigger the sample size, the smaller the sampling error. So that would be 3 ACT points over the square root of 25, so that's 0.6. So that's a standard error for the average. That's going to go right in here. Now, what's the next step? The effect size. So what is the effect size here? Well, the hypothesized value for the alternative is 27.5. For the null, it's 29. So it's negative 1.5. But it's an absolute value. So the effect size, D is equal to 1.5. It's just a distance. So we've got that, and we've got that. So if we're looking here, D is equal to dz times some standard error. Well, we know 1.5. Is that the third question? The next question? So this is C. Excuse me. Now, this is, I guess this is D. And this was B. All right, and C was just the sample average, 27.5. All right, now E. So the effect size in standard units, dz. Okay, great. So here we are. So this is what we want now. So dz is what? So dz is, we know this one is 1.5. And we know this is 0.6. So dz is just 2.5. All right, so that's our distance in z-scores. Now the next question says this. How do we want to get z alpha and z beta? So what should we do? Well, z alpha is set by the significance level. So the next question is if alpha equals 0.5, then what's that going to lead to? We just did that. Z alpha for a one-tailed test, Z alpha, we just did that on the previous problem, is going to be 1.65. So then what's Z beta? Well, Z beta is going to, Z alpha plus, so this is 1.65. So what does that have to be to equal to, the whole thing is 2.5, right? The whole thing together, we said dz is 2.5. So this whole thing is 2.5. So 1.65 plus what is 2.5? So that has to be 0.85. So that means that Z beta is equal to 2.5 minus 1.65, which is 0.85. And these I'm just doing all absolute values. All right, so now we've got that. So then what's the power of the test? Well, to draw the picture, what would it look like? You have to get the power here. All right, so what's the picture look like? Let's just draw it right over here. So we've got these two curves. Here's under the null. And as a z-score, it's 0. As an actual score, it's 29. I'll just stick it up here as our null. So that's our null. And then we've got this alternative hypothesis that turns out to be what, 0.6 standard errors away. So that's going to be, there's 1, 2, no, 2.5. 0.6 is the standard error. It's a z-score of 2.5 away. So this is 1, 2, 3. So it's about right here. Let's just draw it kind of accurately. All right. So we're going to have another curve under the alternative. All right. And this one is 27.5. 27.5 is as a distance. That's our alternative. And so that's H naught. And this distance here is what we've been calling just D, our effect size of 1.5. That's what this is. And then we translated it into a z-score of, what did we translate into a z-score of? 2.5. Right? All right. So that's what we've done. There's dz. So that's dz, and that's d. And then we said, okay, Well, we want to, now we're just going to draw this null cutoff, and we said when we drew it at 5%, we want 5% in this null curve to be here. So that's 5%, which divided this distance here into two pieces. Divided this whole distance into two pieces. I think I can write it better like this. Divided into two pieces. So the whole thing is 2.5, and this piece is the alpha, which is equal to 1.65 in distance. And then we're saying, what must Z beta be? This is Z beta. Well, this has to be what? 1.65 plus 0.85. So that's where we get the 0.85, and that's where we're at. So let's just get some color coding here. So this is our type 1 error of 5%, let's say. When we make this decision, this is like our null cutoff, this is our decision maker right here. It divides it, when the null is true, we're going to be wrong 5% of the time, correct? Because when the null is true, we want to decide on this side. So this is 5% of the time we're going to be wrong. But when the alternative is true, when this part's true, right, we want to decide for the alternative when it's true, but because when it's really 27.5, but there's a distribution around it. So this is the power of the test. This right here is our type 2 error, and that's the power of our test. So now I want to find out this. We've got the 0.85. How can we find out this tail, our type 2 error, and the power? Well, we'd have to look up on this curve, the middle area, between 0.85 and negative 0.85. We have to do that. So this is 5%, but we want to find out what percent that is. So between 0.85, okay, so there we have that. So beta must be what? Beta is equal to, well, you look at the normal table and you'll see that this area right in here is 60%. So that means this is 20%. So beta, the probability of a type 2 error, is 20%, and all this stuff, all that is the power. The power to detect this effect size of 1.5. The power of our test, which is 80%. So our power is 100% minus beta, which is 80%. So that's the idea for this one. Okay, now the next part of the problem says, all right, this is actually a much more common type of calculation. Let's keep everything the same, except, let's say, so we have the same alpha equals 5%, SD, same effect size, and now what n do we need to get power equal to 95%? Remember, we only got power equal to 80%. Now we want to change it to 95%. So the first thing the question asks you to do is calculate beta. So we have, so power is equal to 95% means beta equals what percent? They have to add up to 100, so this is 5%, which means what? That Z beta, this is what we're given here, is going to be what? If it's 5%, it's going to be 5% in each tail, 90% in the middle, so that's 1.65. So now we've got that, and the next, now what do we have? So we have, let's look up here. So we have this and this now, and we have that. So we've got the D is 1.5 still. Z alpha and Z beta together is 1.65 is 1.65 plus 1.65. They're both 1.65. And so now our standard error must be what? So we'll just solve for our standard error. And our standard error has to be, our standard error is equal to 1.5 divided by 3.3, which is equal to 0.4545. That's our standard error, and that's part B, or part C, actually. All right, so I'm just going through these all in one. All right, so now the last thing is how large an n will give us that smallest standard error. So the standard error formula we're using, right, is the standard error equals SD over the square root of n. And we know that the SD is equal to 3. So we have 3 over the square root of n is equal to 0.4545. So now all you have to do is solve for n. Solve for n, and I got, when I did it, 43.57. So that's your answer there. All right, so that's done with that. That's really simple. And let's move on to our next problem. Okay, so let's look at question 4 now. And these are on experimental design, observational studies, and randomized experiments. All right, so a study found that those admitted to the ERs on weekends had higher death rates than those who admitted during the week. So first off, is this an observational study, or this is an observational study because the researcher did not assign people, either randomly or non-randomly, to the ERs on weekends versus the week. Okay, so the next question said, can you conclude causation? Does the study show that it's the quality of the hospital emergency room care that was worse during the weekends than the weekdays? In other words, is there something about the emergency room over the weekend, so the weekend emergency room, is that causing them somehow to die more? Okay? So something about that, is it? Well, if it's just an observational study, you can't conclude that. As opposed to a randomized experiment. If it was a randomized experiment, which would be very hard to do in this case, somebody would have to randomly assign people to either go to the ER on the weekends or go to the ER during the week. But the point would be then that the only thing, those two groups, the treatment and control group, would be alike. There'd be no systematic differences between the two of them. So if they had a higher death rate, one group had a higher death rate during the weekend, then you can attribute it to something that happened in the ER, because to begin with, they were the same. Everything about them was the same, and all sorts of variables, just within random error. Okay? There's no systematic differences, so that if you see this difference at the end, you know it was something that happened after they entered the ER, because everything was the same before. Now, so we don't know. We just know that the treatment, this is like the treatment, is associated with this response. We cannot say whether it's causing it or not causing it. All right. So now the next question gives you possible confounders. Possible confounders, causal links, and neither. Maybe just reasons why people die more, but have nothing to do with the ER or something like that. All right. But we want to, for each one of them, we want to say whether it's a confounder, a causal link, or neither. So let's start with the first one. So it says, hold up. So it says, mortality rates, death rates vary by hospital. Yeah, some hospitals have higher death rates than others. But how would that be? We have to remember what a confounder is. So the confounder would be something else. Something else, a third factor that's both causing people somehow to be admitted to weekend emergency rooms and causing them to die more. Something that happened before they went to the weekend emergency room, before they went to the emergency room, that would be not something that happened after as a cause. So it's a difference between those who, the treatment and the control group, in this case those who go to the emergency rooms on weekends versus during the week. Those are two different groups of people. And it's something that's different about them that's both causing them to go to the, that's changing, causing one group to go to the emergency room over the weekend and the other group not to, and also causing them to die more. So it's something different about people who go to the emergency room on weekends who also are dying more. That's what a confounder is. Whereas a causal link would be explaining something that happens to them in the emergency room, like bad care of some sort that leads them to die more. Or neither. So now let's go back, and what does it say? So, the mortality rates, yeah, they vary by hospital. So what does that have to do with this connection? Really, yeah, some hospitals have people die more than others. But that doesn't explain, that has nothing to do with this problem. So that's neither. Okay, the next one would be what? People may have more serious accidents over the weekend than during the week. So, if they have more serious accidents over the weekend, it's not that the weekend ER is causing them to have more serious accidents. They had more serious accidents first. So they had more serious accidents here, possibly because they were drunk, possibly because they were, if you go to an ER on the weekend, there's going to be a lot of gunshot fighting. There's a lot more violence that happens on the weekend. So let's say they have more serious accidents because they're out acting crazy, and so they get admitted to the ER. And the more serious accidents, like gunshot wounds and terrible car accidents, are going to cause them to die more. It has nothing to do with the weekend ER. This is a marker for people who are having more serious accidents. So in other words, you can remove this, and they're still going to die more, even if it has nothing to do with the weekend ER. Okay? So that would be the confounder. That would be a confounder. Let's look at the next one. Emergency rooms may be understaffed over the weekend because doctors don't want to work on the weekends. So, understaffed would fit in here. You go to the emergency room, and then there's not enough doctors there to take care of you, so you die more. So that would be the causal. That would be a causal link. So understaffed would be a causal link. Would fit in there. Whereas serious accidents over the weekend would fit in here. They happen before they go to the, not after. This happens as a result. They go to the ER, there's not enough doctors, they die. All right, and another one that would fit in there would be less experienced doctors, worse doctors, or less experienced doctors. Maybe more experienced doctors have more choice. They don't want to work on the weekends, so you get the worst doctors and you die more. That's another causal link. And the last one was maybe people who aren't that sick are more likely to wait until Monday to go to the emergency room because they'd rather not waste their weekends in the hospital than those who are so sick they have no choice but are likely to go on weekends. This certainly happens on Christmas. Nobody wants to go to be in a hospital on Christmas, so the people who end up there on Christmas are going to be really sick. They have no choice, and that's probably somewhat of a similar effect on weekends. They'd rather not waste their weekend in a hospital, so sicker. Could be a confounder. Now remember, you have to go by what the explanation here, whether it's true or not, the explanation here, the logic of the explanation will tell you whether it belongs here or there. Okay? So that's it for that one. Now, question 5. Question 5, let me read you the question. A nationwide study examining cholesterol levels in women found that women with 4 or more children had significantly higher levels of cholesterol than women with 2 or fewer children. So, again, observational study, that's pretty obvious. You don't assign people randomly or not to have 4 or more children or 2 or fewer children. So the question is, okay, does the study show that having more children raises cholesterol? Yes, it shows. These are your choices. Yes, it shows definite causation. No, it only shows there's an association. Yeah, it doesn't show causation. You need a randomized experiment to show causation. All right. Which of the following describe possible confounders? Circle yes or no. So, possible confounders. So, first of all, what are we doing here? We're not talking about a causal link would be do more kids, like that, 4 or more kids, something would fit in here would be a causal link. If it was actually causing, does that cause more cholesterol or higher cholesterol? Then people have fewer kids, maybe. Or is there a confounder? Or is there a confounder? So that's like this mystery variable here, this lurking variable that both would cause people to have more kids and cause them to have higher cholesterol. So we're trying to see, this is a confounder, and we're trying to see if each of those choices fits in here. All right, so let's read the choices. Income. All right, we have to read the explanation. Women with more children, with more kids, tend to be poorer. And cholesterol levels tend to be higher among the poor. And then it gives you a big clue. It says poorer to begin with, not as a result of more children. So they're poorer to begin with. They're poor to begin with. And in this country, for some reason, that means more kids. Maybe they don't have other forms of entertainment. They can't afford birth control, whatever. And they just have the more kids. All right? And for the same reason, they're poor and life is hard. They can't eat healthy foods and they have higher cholesterol. So it's not that the kids are making them have higher cholesterol. It's poverty. That works here. But, you know, if I described it as more kids, you have more kids, you get, and that puts you in the poorhouse, and then you can't eat properly, and then you have higher cholesterol, it'd fit in here. So it could be both, but the description, the way it's described, it qualifies as a confounder there. All right, I mean, in real life it could be both, and lots of times things are both. But here, I'm making it simple, and I described it as a confounder. All right, stress. More children cause extra stress that could lead to general poor health, including raised cholesterol. For example, women with 4 children may have less time and energy to prepare healthy foods and to exercise. Well, more children is going to cause you stress, for sure. I mean, yeah. And you don't have time to, you just say, hey, just eat whatever. So, and you'll eat whatever. So that could definitely be a causal link. That would go in here. It wouldn't go in here unless I said more stress, well, it causes the extra cholesterol, but more stress would have to cause you to have more kids. I mean, it could, but I didn't describe it that way. You'd have to say, oh, you're so stressed out, let's just, let's just do it, I can't take it. And you forget to put contraception and you just want to have a good time. Okay, and just forget about everything else. That could do it, but that's not how I described it. That's not how it's described. Okay? So it's not. That would be no. No. That's described. Okay, genetic predisposition. Genes. Cholesterol levels are strongly affected by heredity. So the more children you have, the more likely, what? Okay, cholesterol levels are strongly affected by heredity. Sure, there's a genetic component here. So genes could cause high cholesterol, but then it would have to be the same genes that caused you to have more kids. And that's not what's said here. It said, so the more children you have, the more likely they will be to exhibit a propensity towards high cholesterol. That doesn't even make sense. So that's no. That's neither. Now the last one is age. Women with more children tend to be older on the average, and cholesterol rises with age. Okay, so you out there watching, you're what, 20? you probably don't have 4 kids, right? So, and you probably don't have high cholesterol, right? And people my age are going to be more likely to have more kids and higher cholesterol. So age certainly has to be controlled for. That certainly could be a confounder. It would be very important to stratify to control for age, because age will certainly is going to be associated with more kids as opposed to really young girls. I mean, you're going to have more kids if you're older, and you're going to have higher cholesterol. So that's definitely a confounder. So what you would need to do would be to stratify on that confounder. So you're comparing older women to older women. Then you compare older women with a few kids to older women with 4 or more kids, and you see if there's a difference in their cholesterol. Then you can say, well, that difference is still holding up. But if it disappears, then you would know it was the confounder. Okay? So you want to stratify on the when you have this, which leads us to our next question. Suppose we think that geographical region is a confounder, since both family size and cholesterol levels are strongly influenced by region. For example, South Carolina has both high levels of cholesterol and a high birth rate, while Colorado has low of each. How can we minimize the possible confounding effects of geographical region? All right, so in general, what you want to do is always do this. In general, you want to stratify along the confounding factor. Whatever that is. If it was age, just look at old people, old, middle-aged, young, etc. Stress, you have, then everybody, that confounders are limited because everybody's at the same level of it. So in this case, geographical region, you stratify, and you just look at people in one area, and then what you want to do, you want to compare the responses, the cholesterol level, the response of the treatment to the control group. Within each subgroup. Within each subgroup. So the idea is you want to balance the scales, right? You want to eliminate the confounder and just compare apples to apples. So you'll compare, for example, everybody within the same geographical region, which is all of the choices, split data by geographical region. And then you want to compare the cholesterol levels of the women with a lot of children, compare the responses, which is the cholesterol levels, of the women with 4 or more children to 2 or fewer. And that choice is 4, number 4. So that's pretty much it. And my advice is, so in a randomized experiment, would you ever do any kind of grouping? Well, yes, you could block before you do the randomization. This is stratifying after the results. You could block before because to avoid big accidental differences. There's not going to be systematic differences with randomization, meaning it's not going to always go in the same direction, the difference, but with a small sample size, or if you're interested in some particular factor that doesn't have very many people in it, subgroups, you're going to have to, you could block first and then randomly assign them to either treatment or control, like we did in the computer grading example. Okay, so this is question 6, and the first question asks our best estimate of the slope using these 5 summary statistics. All right, and so A is, so you just need to know this formula. R is SDY over SDX, right? And that's just straightforward. It's negative 0.3 times the ratio. Now, which is y, which is x? You have to read the problem, and it says, what? How do the number of, we're trying to predict GPA from party hours. So, this is y, and this is x, and we have 0.4 then over 4, so we have negative 0.03. That's our slope. Now the next thing I think you'll know how to do, is just ask you for the standard error of the slope, and the formula is given to you. And so it's just the square root of 1 minus r squared. So that's r squared over the square root of n, and your sample size is 49, times the ratio of the standard deviations. So you had a sample of 25 randomly chosen from a much larger population. Which of the following assumptions is not needed for this standard error to be valid? And we got this standard error of 0.014 party hours, points per party hour. GPA is, so it has to be, okay. Slip right? Yeah. So which of the following assumptions is not needed? Well, which isn't needed? We haven't talked about the distribution of the slope at all. So at this point, you don't need normality of the errors. All you've done is calculate a standard error. So all you need to know is the assumptions about independence and equal variance of the errors. We don't need to know that they're normally distributed because we haven't even talked about calculating confidence intervals, or we're not using the distribution of the errors yet, or hypothesis test. All right, so the next one we do use it. It says find a 96% confidence interval for the population's slope using the normal curve. Well, with this small sample size, this is a large enough sample size, I'm asking you to use the normal curve. So I'm either the central limit theorem has kicked in, or I'm just asking you to do the calculation with the normal curve. And you might or might not need the normality of the errors. I haven't given you enough information. But anyway, it says at this point for part D, you want to find a 96% confidence interval. And I just want you to use the normal curve, assuming that it's normally distributed, okay, around the regression line. So what are we going to do? Or that the central limit theorem is kicked in, and so that even though it might not be normally distributed, our standard error is. Okay, so a 96% confidence interval is going to be our sample slope right here. Our sample slope, negative 0.03, and we want to say plus or minus some critical value of z corresponding to a middle area here of 96%. So that means 96% in the middle, and you just have to figure out what this critical value of z is between between z and negative z that gives you the 96%. So you look in the back of the book and you look up under 96% in the middle, and you'll see that that critical value is 2.05. So between 2.05 and negative 2.05 is 96% the curve. So then you're going to multiply that. So that will be your confidence interval. Your standard error for the average will be right in here. And then you're just going to add and subtract that amount. All right. So then it says, suppose you wanted to use the standard error plus the t-curves instead of the normal curve. How would you adjust your answer to part C above? To part C above, to part D above? Well, and to part C too. You'd have to change this standard. Okay, so we'd have to change this right here, this answer. This is our standard error, right? That's our standard error. Now, if we wanted to use the standard, the adjusted standard error, we're going to have to make that larger. By what? So how would we have done that? We would have put a 47 in here instead of a 49, right? So let's just write it. So our standard error plus then. You could recalculate this and put a 47 here, but it's probably easier to just say the standard error plus is 0.014 times what? Well, times the ratio of, you want to get rid of that square root of 49 and change it to a square root of 47, so you could just do that. And that will make it somewhat bigger. All right, so we do that, and then let's say you want to use the t-curves. Well, how many degrees of freedom would you have? Well, the degrees of freedom are equal to the sample size n minus 2. So in this case, that would be 49 minus 2, which is 47. And then finally, it asks you, how would the critical value of t compare to the critical value of z? Well, remember, the t-curve is fatter in the tail, skinnier in the middle. So you just want to know where the critical values are quick. Let's just do a super exaggerated version. Let's say that was z, right? And we want to do a confidence interval of whatever. All right, let's say right there is 96%. Now t is fatter. I'm going to do a really exaggerated version, but imagine being fatter is not as tall, right? Well, in order to get out to 96%, it's smaller here, so you have to go out further. So the critical value of t, the t star, the t between t, and negative t to achieve the same confidence interval. Look, it's skinnier here. This is the t. It's shorter here. It's fatter there. It's both 100%. And this is the z. So if you want 90, you're going to have to go further to get the 96%. So the t star is always going to be greater than the z star, even though the t stat is smaller than the z stat. So that looked horrible. Here, let me just show you. All right, so this would be if you have a negative z and a positive z here. And that gives you the 96%. To get the same 96% with the t, you'd have to go out further. That's all that is. Okay, so now this is question 6 continued. We're going to compute the z and t statistics. Now, remember what we did before? What we did before was we saw that for the same confidence interval, the critical value of t is greater than the critical value of z. But now we're going to look at how the t-stat compares with the z-stat. So let's look at, remember the formula. So z is r over the square root of 1 minus r squared times what? R over the square times the square root of n. Okay? Whereas t is equal to the same thing, r over the square root of 1 minus r squared, but not times the square root of n. We have to adjust that. This t statistic is a little bit smaller than this one. And this is the stat. This isn't the critical value. The t statistic is by a factor, this is n minus 2 instead of n, where n is the sample size. We're doing the same problem from before. So n was, let's remember what it was. So r is equal to, it's the same problem as before. So r was equal to negative 0.3. So you have negative 0.3 over the square root of minus negative 0.3 squared. This is, you don't have to worry, it's going to be squared. So it's just that minus squared times the square root of 49. N was 49. And this one, that worked out to be approximately, what did I get? Negative 2.201. All right, but I think the instructions said round to just 2 decimal places, so that's fine. Now, how are we going to, now when we look at the t, what's the t going to be? Well, we could just multiply this by what? We could multiply this by, we could take this, negative 2.2. I suppose we should leave all the digits in. I think it was negative 0.2014. And then we're going to multiply it just to get over to this one. If we wanted, we could just put a 47 in there, but if we already have that one, we can just what? Divide it by square root of 49, so that would cancel out. and then multiply it by the square root of 49 minus 2, which is that. All right, so it's smaller. And when I did this, I got negative 2.156. I mean smaller in absolute value. All right, so that's our Z and that's our T. Now, what do we want to do with these? We want to compute p-values. So the p-value for, what's the p-value going to be? To test the null hypothesis with the alternative, and remember, the alternative here is beta is less than 0, so that's one-sided. So we're just going to look at one side here. One side between what? Between negative 2.2 and positive 2.2. So let's go, if you look on the normal curve, you'll see that on the table that in the middle is 97.22%. So on each tail is going to be 100% minus that divided by 2, so that's 1.39 on each tail, but we're only concerned with this one, so 1.39%. All right, that's for using the Z, and then you also want to use the T. So first, the T is a whole series of curves, so you have to say how many degrees of freedom. So the degrees of freedom is n minus 2, which is 49 minus 2 is 47. But then basically it's too complicated to look through all the, to give you all the, the T tables would be too cumbersome on your exam. And so instead, and you don't have a p-value calculator, so instead we're just going to answer the question, will the p-value be greater than, less than, or equal to this, to what you got for the Z? Think about it. Will be greater than, less than, or equal to? Well, the p-value is always going to be greater than, because the p-value with T is going to be greater than what we got before. So the answer, the p-value for T will be greater than the p-value using Z. Why? Because remember, the curve, because it's fatter in the tails, the T curve is going to have more area in the tails, and the tail is what your p-value measures. So it's going to be greater, which means you need stronger evidence to reject the null using that T. All right, now your last question is same as above, but now assume the alternative for both the Z and the t-test is two-sided. So how does it change? If we, instead of having that, we would have not equal to. Okay, so how does it change? So if we just did the same thing, and we said, did a two-sided test, so for two-sided, what are we going to do? This is one-sided. Well, what do you think we'd do for two-sided? We'd count the area in both here, right? Because it could fall on this side or this side, so we'd count the area in both. So for two-sided, we'd double that. It would be both areas. It would be 1.39% plus this one, that area, which is 1.39%, right? So plus 1.39%, so we double it. Both tails, that would be two-sided. All right, and for T, it would be the same thing. We would double, it's a multiple choice, and you would double the percent for the one-sided test. Okay, so that's pretty much it, and I'll have office hours Friday from 4 to 6, and again on Monday from 3 to 6 extended office hours. So see you. Bye.